At 35,000 feet, everything about an airplane feels precise. Every sound, every movement, every part working exactly as it should. But hidden inside that precision is a quiet question most people never think to ask. Why are the engines there? Why not closer to the body? Why not on top of the wings? Why do some aircraft hide them at the back, while others hang them underneath like heavy weights? It might seem like a small design choice, but in reality, this single decision changes how an aircraft balances, how it flies, and how it survives failure. Because in aviation, even a few meters of difference can completely reshape the physics of flight. To understand engine placement, we have to strip flight down to its basics. A jet engine does one job. It produces thrust. That thrust pushes the aircraft forward, allowing air to flow over the wings. And the wings, through that airflow, generate lift. So the engine doesn't actually hold the aircraft in the sky. It simply makes flight possible. But there's a detail that matters far more than most people realize. Thrust is not just about magnitude, it's about location. Where that force is applied changes everything. Think of it like pushing a shopping cart. Push from the center and it moves straight. Push from one side and it starts turning. Aircraft behave the same way. If one engine fails, thrust becomes uneven. One side continues pushing, the other doesn't. And the aircraft begins to rotate, yawing toward the failed engine. Pilots counter this using the rudder. But how manageable that situation is depends heavily on where the engines are positioned. And that leads to one of the most important constraints in aircraft design. Every aircraft must obey a simple rule. It has to be balanced. Not just roughly, but precisely. Imagine the airplane as a long beam in the air. Somewhere along that beam is the center of gravity, the point where all mass is balanced. And somewhere else is the center of lift, where aerodynamic forces act. For stable flight, the center of gravity must sit slightly ahead of the center of lift. This creates a natural restoring effect. If the aircraft pitches up or down, aerodynamic forces bring it back toward equilibrium. Now introduce engines into this system. Modern turbofan engines are enormous. Each one can weigh several tons. Placing that mass incorrectly doesn't just reduce efficiency, it destabilizes the aircraft. Too far forward, and the nose becomes heavy. Too far back, and the aircraft constantly wants to pitch upward. So engineers aim to place engines close to the aircraft's structural core. And in most designs, that core is the wing. On modern airliners, engines are mounted under the wings for a reason that goes far beyond appearance. It's about structure. Inside every wing is a reinforced section called the wing box. This is the strongest part of the aircraft. It carries lift forces, fuel weight, and structural stress during flight. By attaching engines directly to this area, engineers use an already strong structure to support one of the heaviest components on the aircraft. But there's another, less obvious benefit. In flight, wings naturally flex upward due to lift. This creates stress at the point where the wing meets the fuselage. Now imagine adding several tons of weight beneath the wing. That downward force partially offsets the upward bending. In effect, the engines help stabilize the wing itself. This allows for lighter, more efficient designs. Then there's engine size. Modern engines are built for fuel efficiency. They use large fans to move massive volumes of air. The larger the fan, the better the efficiency. But that also makes the engines physically enormous. Mounting something that large on the tail would introduce major structural complications. Under the wing, there's space, support, and balance. There are also operational advantages. Fuel is stored in the wings, so delivery to the engines is simple. Maintenance crews can access engines without specialized equipment, and turnaround times are reduced. But even this widely used design comes with compromises. Mounting engines under the wings introduces new risks. The most obvious is ground clearance. As engines grow larger, they sit closer to the runway. This increases the chance of foreign object damage. Small debris, stones, fragments, even ice, can be pulled into the engine at high speed. And at those speeds, even minor impacts can cause serious damage. There's also the issue of asymmetry during failure. Because engines are positioned far from the aircraft's centerline, losing one creates a strong rotational force. To counter this, aircraft must be designed with large vertical stabilizers and powerful rudders. And then there's thrust-induced pitch. When engines sit below the center of gravity, increasing thrust tends to push the nose upward. Reducing thrust has the opposite effect. Pilots constantly adjust for this interaction. So while underwing engines are efficient, they require careful control and design considerations. Now consider a different type of aircraft, business jets. Here, the wings are clean, no engines interrupting airflow. Instead, the engines are mounted at the rear of the fuselage. This configuration solves a different set of priorities. A clean wing allows smoother airflow, improving performance, especially for smaller aircraft. Engines mounted high above the ground are far less likely to ingest debris, making them ideal for operations at smaller airports. And because the engines sit behind the cabin, much of the noise is directed away from passengers, creating a quieter experience in the front. There are also design advantages. Without engines under the wings, more surface area is available for flaps, improving low-speed performance. And many of these aircraft sit lower to the ground, allowing built-in stairs. In that configuration, there simply isn't enough clearance for large underwing engines, so they move to the tail. But this solution introduces new challenges. Placing engines at the rear shifts weight backward, affecting the aircraft's center of gravity. Engineers must carefully balance other components to compensate. Fuel systems become more complex, with fuel traveling longer distances from the wings to the engines. And then there's the T-tail. The horizontal stabilizer is mounted high above the wing. In normal conditions, this provides clean airflow and strong control. But at high angles of attack, the wing can disrupt airflow to the tail, reducing control effectiveness. In extreme cases, recovery becomes more difficult. To prevent this, some aircraft include systems that automatically push the nose down before reaching dangerous conditions. It's another example of how solving one problem creates another. There was also a time when two engines weren't enough. In the early days of jet aviation, engines were less reliable, and regulations were strict. Aircraft with only two engines were not allowed to fly far from diversion airports. This made long-distance routes difficult. Airlines needed redundancy. 4 engines provided it, but at a cost. More fuel, more weight, more maintenance. So engineers developed a compromise. 3 engines. Trijets. These aircraft offered improved safety without the full cost of 4 engine designs. For a time, they dominated long-haul travel. But technology improved. Engines became more reliable. Monitoring systems advanced. And new regulations allowed twin-engine aircraft to fly long distances safely. With that, the third engine was no longer necessary, and the trijet quietly disappeared. Airplane design is never about perfection. It's about balance. Every engine placement, under the wing, at the tail, or even 3 engines, represents a different solution to the same problem. How do you balance efficiency, safety, structure, and cost? There is no single answer. Only trade-offs. And that's what makes aviation so fascinating. Because something as ordinary as where an engine sits is actually the result of decades of engineering, compromise, and evolution.